right, thank you, everybody. Now, 2 Germans called Max in a row. How much better can it get? Okay, I'm Max. I work at People. I'm still doing a project at the Rabobank, so some credits go to them about transaction monitoring, where we're building an automated solutions to classify fraud and transactions. And one big part of this was looking into explainable AI to try to understand our model and really see how we make predictions. So that's what this talk will be about today. We're going to have a brief look at transaction monitoring in general. What is it even? Then look at the basics of SHAP. Have a quick look at how to implement this in Python. And then dive into the different graphs you can get out to really understand your model on a global and a local level. Finish up with how we translate this from something that we understand to a more, let's call it human readable output for an analyst, for example. Let's get started. Transaction monitoring, well, we all know it. We're human beings, we have phones, we send money to friends, business, whatever, online shopping, Black Friday. In practice, of course, money goes to an intermediary, your bank, and gets sent through. Many people do it, and of course, there are some black sheep involved. So that means, by law from the Dutch National Bank, every bank is obliged to monitor every single transaction for terrorism financing and for money laundering. It's quite a big task. There's various systems in place that can be from really manual inspection, automated rule-based systems, but also now looking more and more into AI systems. Monitoring is required. The Dutch National Bank has their own thoughts about AI solutions. They're a bit more conservative than we are, but they're slowly warming up to it. But in any case, whatever you do, you have to really monitor your solution and be able to explain how you come to outcomes. And this, of course, where explainable AI or XAI comes into play. You might ask yourself, okay, I have a model, I have great output, 85% accuracy, what do I know? Why should I spend more time now on XAI? My answer would be, it can really be used to improve your model even further, which maybe is not the key thing, but really what it helped us with tremendously is really to understand our data and really get more into the depth of it to get to know the model, how does it make decisions, and how the changes in data also affect the model outcome. So that's already quite important. And you can use it in the end to explain the model output to an end user, if you have one. And lastly, maybe not the best reason, but it was mentioned before, the EU AI Act is up on us soon. And that will likely mean that we all have to explain our models by law. It's going to come. And that means we don't have the simple data black box AI model output diagram anymore, but there will be something in between. And then, to sketch this a little bit, now maybe the first question you would ask yourself, do I really have to explain my output? If not, well, then I think the world is yours. You can go all crazy and use any kind of model you want, looking at the previous talk. If you do want to explain your data, you can make a cautious choice to pick a model which is really inherently explainable. So this would be, for example, something like logistic regression, KNN, or trees, which then maybe not have the performance that you need. So if you go to something different, then you need XAI methods, really. And in general, I would say there's 2 choices. One would be to pick something that's very specific for your model. Attention, gradient latency. Or you say, no, let's pick something very general. For example, SHAP, perturbation, or Lime. And in this case, we're going to focus on SHAP. That's what we picked. Reason being why we picked SHAP is that it's a very unified framework and can be used for many models. It's model agnostic, and we hope to scale this also into different solutions in the bank. It can be used for global and local explainability. It's by now quite widely used and well documented. So Stack Overflow is your friend. And it is relatively fast and extremely easy to use. Before I show you how to use it, let's have a very quick introduction. What is it? What does it actually do? So SHAP calculates SHAP values, and you calculate a SHAP value for every feature. And basically, the SHAP value is nothing more than the model output with your feature minus the model output without your feature. So then you get to know already how important is this one feature for my model. In practice, if you look at any common, I don't know, classifier like XGBoost, yeah, your features are fixed, so you can't really remove a feature. But there's a smart way to tackle this. We don't really take them out, but instead we make them random, and then such they don't have any predictive power anymore. And if you want to do this properly, you have to do it for every feature subset. And yeah, to maybe show this a bit, imagine you have a model with 10 features, then you could make a subset S1, where you make the feature 1 and feature 5 random. You can make one where only the second feature is random, and so on. However, if you have 10 features, you end up with 1,024 subsets. It gets quite expensive computationally, and that's not even a lot of features. So what do you do? Well, luckily, SHAP includes approximations, so in the end you can reduce this to a linear problem and then make this into something that you can actually use practically every day. Okay, so that's what we do. We want to calculate these SHAP values. How can we do this in Python? I tried to make a very basic example of how you could make such a classifier model from beginning to end. Let's assume we want to classify penguins. We all like those. Maybe some people like cats more. We load our data. We have to define X and Y data, so data and labels. Sorry, wrong button. We split this into training and testing data, and quite important later on, if you have numeric and categorical features, you want to distinguish how you pre-process them. So let's write down which ones they are. And then, to train our classifier, let's make a simple pipeline. So first of all, we take care of numeric features, apply a simple imputer and a scalar. The same thing we have to do for categorical features. Again, the imputation, and in this case, we do one-hot encoding. We have to combine this all somehow. For this, we can use a column transformer, and we give this the two pipelines and the feature names. So then this guy knows already what to do with which feature column. And then lastly, we can make a final pipeline, train a model, fit the training and testing data, and we have a XGBoost trained model. Okay, nice. We have a trained model. Now let's get to actually calculating SHAP values. Before we can do it, we have to get our model out of the pipeline, because we need really the trained model. And if you have the model itself and you would use it in SHAP, you would get graphs with very obscure feature names, because the model itself doesn't know what a feature is called. So you would have a graph with feature 1 to feature 10. Would be quite hard to find out which feature has importance in the end. So we make a list. It's really just a list of all feature names. There's a few more lines because we have to collect all the one-hot encoded features. We update our model to set the feature names in the model. And then as the last step for preprocessing, and now we're almost there, let's apply this imputation pipeline that we created before on our data, that we have the right scaling in our data. And now we have all we need. We have a trained model with feature names. We have data in the right format. And we can throw this into the SHAP explainer. And it's only 2 lines. That's the nice thing. It's very easy. First, it's an XGBoost model. So we pick the tree explainer from SHAP. Then we have it, and the next step is only to tell it, okay, go ahead, calculate the SHAP values. And I think the only really important things to consider is, if you want to do it, is one, watch out for categorical features. If they're one-hot encoded, and secondly, that you work with rescaled numerical features, so later on, if you look at your graphs, to keep this in mind. Okay, now we have all the SHAP values for the features. What can we learn? I think now it really we can dive into our model, and the first thing we're going to look at is global explainability. So really understand what does the model do as a whole, which features are responsible for model predictions, and also how do changes in features change the model output. And then on the right-hand side, you see a graph with all the features. There's some combi feature, then maybe we know for a customer, is he a warlord, drug dealer, Brabantians are quite famous for drug dealing and money laundering, so it's important to monitor. But what you see in the end is the SHAP value for the first feature, this combi feature, is huge compared to anything else. So basically, any decision made by the model will be made depending on this one single feature. And what we actually saw during model training, we had a model with 100% accuracy, so we had already all the alarm bells ringing. Looking at this, it also became clear why, that this one feature makes all the predictions. And when we narrowed it down to the feature, we had a look at it and noticed we actually have data leakage from the labels into the feature, and we had to then refactor or take out this feature and then retrain the model. So we did that. This guy went away. We retrained the model, reran SHAP, and we got to something like this, which looks a bit more sensible. Still some things to learn. First of all, if someone is a warlord, the SHAP value is very high, so that's apparently a good indication if someone is or is not a money launderer. Still the strongest feature. Then you could again check, does it make sense? Is my data good? Is something wrong? Should I refactor this feature? That's really up to you as a data scientist working with the data owners. And secondly, if we look at the last two features, if someone owns a yacht or has one or multiple houses in Luxembourg, apparently this has almost no contribution to the model output. And then you can use this to really decide, for example, do we want to keep these features? You could kick them out of your model, retrain it, evaluate the performance, and then possibly make your model simpler, which, at least for us, having a model in production is quite important to have the simplest possible model. Okay, now we know kind of what is important, but we don't really know in which way. Does it push it to making positive, negative predictions? And that's what we can use the feature sensitivity plot for. Let's first have a good look of what it tells us. So we have colors here on the right. They tell us if a feature has a high or a low value. And then on the x-axis, we see whether the prediction pushes the model to a positive or to a negative prediction. So for example, looking at the first feature, if someone is a warlord, it pushes the model to a high SHAP value, meaning a positive prediction, so likely a money launderer. If someone is not a warlord, blue color, likely he is not a money launderer. You can also see for the warlord feature, it's quite nicely separated. There's a big gap. And you can make a clear distinction depending on the feature. One thing that we learned, which surprised us, if you look at the owns yacht feature, you can see that if someone owns a yacht, so red color, it's actually more likely that he's not a money launderer because it pushes the model towards the left. And if he does own a yacht, he is if he does not own a yacht, he's more likely to be a money launderer. So it's kind of against the initial thoughts we had from the data and discussions with data experts, which led us in the end to the fact to remove this feature until we understand the data better and can make more sense of it. Then I want to show you one more plot for global explainability. Namely the decision plot. Decision plot is also, it's maybe a bit more tricky to follow. What you see here is individual lines. Each line is one single prediction. The x-axis at the bottom shows you the model output. In reality, there would be more features, and you see a convergence at some point to the average model output, which would be, it's a binary classifier, so 0.5. The y-axis are the features. They're ordered in, from top to bottom, descending importance, so the most important ones at the top. And then if you follow a line, a single prediction, then at each feature, the SHAP value from this specific feature is added, and you arrive at the end, at the top, at the final model output. So what you can do is you can follow either a single lines or a group of lines to understand how features influence this group of predictions. So for example, if we take this strain here, we can see that the final feature, the warlord one, pushes them all far to the right. And how can you use it? Yeah, for example, you could pick a few false predictions that you want to gain more insights, and then you can find out if there's like a common feature driving them all into a certain direction of the final model output. Okay, now we kind of understand what happens on a global scale, but you can also use SHAP to look at local explainability. And this can really tell us how did the model come to a very specific outcome, and what are the contributions of individual features for the specific outcome. And in SHAP, there are 3 plots available for this. There's the local bar plot, the waterfall plot, and the force plot. They all tell more or less the same information, but then in a somewhat different representation. Let's start with the local bar plot. It's quite similar to the global bar plot. You can see basically each feature is really off of one single prediction. So you can also see the value of the single prediction that the feature had. So you can learn, in this case, you would sum it up. You see it's a non-money laundering case because the SHAP values on the left side, they dominate. And you can see which features would be dominant for the single prediction. Personally, yeah, I prefer the next plot because I think it's more insightful, which would be the waterfall plot. Again, it's more or less the same, but then what you see is that you start at the bottom at the x-axis. You start at your base output, so again 0.5 in terms of probability, and you add feature by feature the SHAP values till you come up at the final model output for this case. What can you learn? Yeah, this case was certainly a non-money laundering case because you have a negative output of your model. The customer is a warlord, and this cancels out the fact that he's a drug dealer and he had a previous alert. Yeah, then looking at it from a data perspective, the question would be, okay, does this feature make sense, especially the top one? Because from a analyst perspective, yeah, we found out that if he's a drug dealer and he was flagged before, it's actually quite a strong indication. So probably this is a false negative and should be flagged differently. So you can use this to really understand your data, understand your model, and see how you came to predictions, and use also for in-depth discussion with your analyst, in our case, for example. And then the last plot, looking at local explainability, is the force plot. The force plot shows, again, for a single prediction, the outcome, but then in an additive force layout. So you can see all positive SHAP values on one side, all negative ones on the right side. Yeah, in this case, this person liked online shopping. Was the dominant factor that it was a money laundering case. And yeah, it was, again, not a money laundering case because he wasn't a warlord. He didn't live in Brabant, and he was also not an influencer. So, I mean, that's a very strong indication. And yeah, obviously. And if you haven't noticed, these are, of course, not real features that we would use in a bank. But yeah, I had to censor what we actually used because it's yeah, somewhat of a business secret to not allow you to circumvent the rules we have set up. Okay, now looking back, I think by now we can say, okay, like on a global level, how did we come to a decision? On a local level, we can dive into single predictions to understand how we make decisions. Use this, for example, for false predictions to understand where it's going wrong. But if I didn't lose you yet, and you look like this, you would have certainly lost your model end user. In my opinion, SHAP is really a great tool, but it's really a tool for data scientists. It's for us. It's not for a novice. And to explain the model to the end user, we need something somewhat different. In our case, there's really an analyst, a person somewhere. He gets a model output. He has to use this in his evaluation, and only a score or a rating is not enough. So he has to know, why did this model come to a certain prediction? We are somewhat limited. What we can provide them, it's not. There's no Power BI. There's no fancy web dashboard. It's literally just create some Excel or text files that they get. So we had to work with this to try to make a translation from SHAP values to something that they could use in their actual daily work. And our solution was quite simple. What we did in the end is we created a dictionary, or actually two, where we had just a textual explanation of each feature that we have. And we do this for high and low values. So the high one being, if you are or if it is a money laundering case, we pick the top dictionary. If it is not a money laundering case, we pick the low dictionary. Second step, let's look at a single transaction. What was it? Let's assume it is a money laundering case. Step 3, for the specific case, we find the top 3 features, but not absolute, but really specifically the top drivers for this position that it is a money laundering case. And fourth step, simply get the predicted outcome of the model for the single case. And then we can put this all together. And this is basically what we also in the end supplied to the end user of our model. So he just gets a nice output saying, hey, look, we're quite convinced this is a money laundering case with a certain probability of 75%. Reason being he's a warlord, he's a drug dealer and an influencer. I can't get much better than that. And then that's something that they can work with and also validate their data and check if it actually all makes sense. And yeah, I think here it looks a bit simple and stupid. In practice, our feature names, they're a lot more complex. There's a combination of different data sources to make up features. They're a lot more obscure. So if you would simply give them like a feature name and a value, for them it would simply not be sufficient. So we had to make this kind of like a translation step in between. Now, to already sum up slowly. For me, the main takeaway is that SHAP is only one tool. I mentioned in the beginning. There are more tools out there. SHAP might not fit your problem, but if you want to start somewhere, it's quite a good start. You can use it even for an LLM, for that matter, to understand how the next word predictions are made. But also maybe keep in mind, it doesn't replace other tools. So if you look, for example, at a correlation matrix, like the most basic data analysis tasks, you should still stick to those and really see this as an additional tool in your toolbox to extend your knowledge and your depth of insight that you can gain from your data. Secondly, I hope I could show you a bit what is global feature importance. Just keep in mind it's like about the global view on your model, how does it come to decisions, how do specific changes in features affect your model. But you can also use it for local feature importance, so really understanding a singular prediction, including all your data of how this decision was formed and made. And maybe the most important point, we started out with this really because it was a requirement for us. We had to be explainable for compliancy. But in the end, we actually kind of fell in love with it, and really glad we used it. It really gave us tremendous insights. Really, we understood our data better. We had a great tool to communicate with the model user in the end, and now have a much tighter collaboration because it's kind of a platform that helps us communicate and speak in the same language. I think there's many reasons to use it. I would encourage everyone to add it to their toolbox if you haven't done so already. With this, I want to thank you for listening to me. And I think there's some time left for questions. And in case there shouldn't be enough time, then I'm around here. Or you can also contact me via phone and email. And I'm happy to elaborate further. Thank you.
We do have time for questions, so okay. I think the person in the back first.
Nice one.
How do you do it for a multi-class data?
The same basically. So the SHAP does support multi-class. You can actually, the example of the penguins would have been a multi-class model. I can also make this available on GitHub if anyone wants to download it. It's open source data. Only your plots get slightly more complicated because you have a multi-class problem. But it's the same methodology.
How is it the same? Do you do one vs rest, or one versus the rest for all of the classes, or how is it different?
No, you get. I only looked at it very briefly, but you would have then different, for example, barcode, different colored bars depending on the predicted class to tell you how much the feature influence or the feature drives a certain class prediction.
Okay, there were two people in the front. Can you pass on? Great.
All right. Thanks for the talk. Maybe a bit more a question, a bit more on the technical side, but to me it seems like calculating a SHAP ratio is highly dependent on the actual inference that you choose for the model, right? So you choose an inference, you put that through the model, and then you vary the features, and you look what the impact is on the actual prediction, right?
Yeah.
So the selection of the data that you use to inference seems very important to me, and I'd like your thoughts on the following scenario.
Yeah.
So what happens if do you calculate SHAP values as a mean? And if so, what happens if you have an activation, a feature that is low probability, but high impact? Because in the mean, it wouldn't show up as a big impact, but it would be very important for certain scenarios. So do you deal with those types of questions at all?
To be honest, I didn't deal with it specifically for this project. I think it's maybe a general problem if you look at model training, because if you have low occurrence with high impact, your model is not, I don't know, say used to it. So the question is very general of how much will your model learn if you don't have sufficient data available.
Well, what I mean is it has learned.
Yeah, it has learned something, yeah.
In a specific context that it's very important, right?
Yeah.
But only in that specific context.
It's a good question. Yeah.
Well,
to be honest, I don't have a very good answer, unfortunately. I think it's certainly something to look into. It's not something that we encountered. But yeah, my tip would be if you have this data and you know it beforehand, then it sounds like you have quite some deep domain knowledge ready. And then it would be something that I would specifically look out in the SHAP values also to see if you can see this being really reflected in it.
And do you calculate SHAP values by calculating a mean over different inferences, or do you look at individual?
So you can calculate them for individual predictions in the end. Yeah, so you do it for all feature subsets, for all data. You can obviously you have local importance, right? So you can really calculate for a singular prediction. You can calculate your SHAP values.
And do you then use them as a mean?
And then if you would have there maybe a singular prediction with a very high. Where there is a feature where the model knows it has a high predictive power, then on the global level, I think it would be probably, now think about it, on the global level, I think it would be averaged out, possibly. But then if you look at a singular prediction, where the model also comes to the conclusion that this feature is important, then you should be able to see it reflected in the local plots.
Right, so then you could use the local plots and kind of plot the the distributions over the features.
Could also be a check, so like a sanity check, right? Because you that's what you want, basically, right? Let's assume you have this feature, you know it's I don't know, a number of chairs in your house, is super important, and you know this is very predictive, but it doesn't happen very often that this feature occurs. You could then probably check on a local level where this feature does have, for example, a positive value, if it actually drives the model strong in this direction where you would expect it to, or not.
So it's important to keep that in mind, I guess, when using the global SHAP values, because it could fail silently.
I think it could just like smoothen it out, basically. Yeah, indeed.
Okay. Thank you for your.
So I think it's also maybe just one follow-up comment. Really important to use as a tool to really dive into your data and try to understand and see what's happening. And there are, I think edge cases. If you know them, it's something to really consider. But then also, where your model makes right choices, maybe not even the most important, most interesting thing to look at, but look at where does it go wrong? False positive, false negatives. What drives these? Are there like clusters where like one feature, like this is Warlord example, it's just dominating anything else. So even if all the flags would point towards money laundering, if this guy is negative, you will still end up with a non-money laundering case, which is not what you want. And then how do you counteract them? Would you have to tune your model weights, for example, or this feature weight?
Well, thank you for the awesome answer.
Can you pass it to the back?
Oh boy. Maybe in stages, but we'll see.
Nice.
So, yeah, thanks for the presentation. I actually wanted to ask, were you forced to not use certain advanced neural networks because of SHAP not being applied to those? So
Not directly, no. So let's phrase it like this: anything is allowed as long as you can explain it. That's, I think, how I would phrase it. Yeah, we did experiment also with different types. So yeah, just logistic regression, which was worst performance, so it was out. Yeah, XGBoost is semi-explainable, but SHAP to the rescue. We didn't try anything much more fancy because performance was already good enough. So we literally stopped there. But there was no fixed restriction saying this is like the most advanced you can go. I think, at least for us, as long as we could explain it satisfactory, whatever that means then for you, we were good to use also other types of models. Yeah.
okay, thanks.
Any more questions? Yeah. Can you pass it to the front again? That's easier. Oops.
So thank you for the talk. I have a question whether this is just an illusion of explainability, because at the end of the day, you don't know why you have such SHAP values as you do.
Yeah.
It's just like you know which features drive your model, but you don't know why. You don't know why those features and not different ones.
Yeah. Good question. Illusion. Yeah. Well, maybe it's good to look at it this way, that you can understand how your model came to prediction, right? And you can understand which feature has an influence on it. Yeah, if that answers your why question, I'm not sure. Judging by the question, maybe not. So maybe then you have to go either deeper or pick really a inherently explainable model to answer these questions. Yeah, looking at, like, I mean, you could use this, like I said, for an LLM to understand the importance of I don't know, some next predictions. So you would get an understanding or feeling of maybe with which weight or importance this choice was made, but certainly not the why, right? Because that's too far buried down and too abstract, I think, for us to comprehend.
So for an inherently unexplainable model, we can just get like brief explainability,
well,
semi-explainability.
Yeah, let's say, I would say like this is like the level that you stay at. So you you can understand of the importance of your data and the influence and of your features and how they drive your model towards predictions. And I would say typically that's enough. I can imagine the case where if you really want to develop your own deep neural network and then something goes wrong, you maybe want to really dive super deeply into it and understand, okay, why does it not recognize this? It should be obvious, maybe for us as a human it is, but then not for the model. But then I would say this is not the technique that you have to go for. Then maybe you need something a lot more model specific to understand these like more fundamental questions.
And then a follow-up for that, which level of explainability is required by the EU law?
That depends on your model. Very good question. So also the EU Act is not yet in place, and I'm not an expert, but from my, at the moment, layman understanding, there will be a different categorization of model type, depending on the risk that the model will pose, and depending on that, there will be an requirement for explainability, but the EU AI Act is written in a very abstract language, so there's a lot of room for interpretability. Yeah, it depends on the domain you work in. For us, what it would literally mean as a bank is that we have to consult also with legal experts, and then yeah, with Dutch National Bank, with all the other banks, we would probably collaborate to kind of yeah, work out these more practical standards of implementing the EU AI Act. But it doesn't say, oh, if you do XGBoost in a bank, you have to use SHAP at the least. That's no. It's like very, yeah, not shallow, but more abstract and more unclear at the moment. Yeah.
Thank you.
So sorry, that was the last question. I would love to ask more questions from Max, but we have less time for the next talk. So I would like to thank Max again for the presentation and coming here. And huge round of applause for Max again.